Then the next one, you can see the diagram here. So this diagram is just telling you, okay, now you can see what I've done here. Look at this. You see I divided it into two. So I would remember that this is a concrete wall. So I just divided it into two to make it easy for me to calculate the area. This is a trapezium, and you know the formula for a trapezium, but you can divide trapezium into two to have a rectangle and a triangle. Okay, now you can see this. If you look at this, you see now this is telling you the weight. This x1 is these drawings will be very important when I start determining when I get to this point. When I want to determine these values, that's when this drawing will be so important. But the only reason I divided this into two is because I want to calculate the area here. So I just want to calculate what is the weight. If I want to convert unit weight, which is in kilonewton per meter cube, I want to convert it to force or to weight in Newton. I will multiply by area. Sorry, I'll multiply by volume. So I have kilonewton per meter cube. I want to convert this parameter to kilonewton only. So what I will do is this. I will say this, I'll multiply it by this. And that's very simplistic, because now I want to do this because the wall is very long. You don't know the length of the wall. So in civil engineering design, we are going to design per meter length. So that's why here we see 6 times 24. It's not just 6 times 24. This is 6 times 24 times 1. Because we are designing the wall, we know that this wall stretches in this way. So we can't say this is the actual length, because we are not giving the length of the wall. So when you want to design per meter length. So with that per meter length design, you can extrapolate to how many meters length your wall is. So as simple as it is, you know the area, you want to know if you multiply the area or the volume of the rectangle, which is length times width times breadth, and you know the length already, you know the width already. So if you multiply 6, which is this value, the length of the wall 6, multiply it by 0.5, this is for W1, and multiply by this 24 stands for unit weight of concrete. This is the unit weight of concrete, which is 24 kilonewton per meter cube. So you will get 72 kilonewton. So you do also for the triangle part, and the triangle part is very simple. You already know the area of a triangle. The area of a triangle is half base times height. And what is the height of your wall? You know the value for the base. Now you see the height here is 6 meters. The base is 3.5. So you see 3.5 is for this 3.5. How do you get this 3.5? The whole of this place before is 4 meters. We know this place is 0.5. So if we divide this thing down with a straight line, this place becomes 3.5. It's not giving you the question, but with common sense and with your engineering knowledge, you can be able to get it. So when you get this 1 over 2 multiplied by 3.5 times 6 times 24, you will have 252 kilonewton. So you will basically, to find the whole weight of the wall, you are going to say the weight of W1, add it with the weight of W2, you get the weight of the wall. Conversely, or otherwise, if you don't want to go through this whole length, you could also go through this method and use the formula for area of a trapezium. And the area of a trapezium is half in bracket multiplied by half multiplied by bracket, even bracket b. You have the big B here and the small b, close bracket, multiplied by the height. With the same, if you go the same way, you will get this value will be the same as this. I don't need to explain this thing more than once. I believe you should understand this is not that very difficult. Okay, so we move to calculate the location of the resultant of this force from O. So you see, we are assuming that if this wall wants to tip over, if you push this wall from here, that we are assuming that it is going to actually rotate in this way. So if the wall is going to rotate, if we are pushing it this way, so we are calculating the rotation of the wall from this point. So we are calculating the moment of the wall about this point. And you know that moment is force times perpendicular distance. So we are calculating for using Rankine method. The only difference with this Rankine method and this, like I said, is the value of the lateral earth force. As simple as it is, you know, okay, now if you want to calculate your value for the lateral, the moment, so how will you calculate this? You know, for the first diagram here is W1, and that is the triangle. So the distance of W1 to this point. So what is the centroid of a triangle? Is L/2. And that is why we have 0.5/2 for this place. So the centroid of this particular shape is L/2. So we now have 0.5/2. We'll add it with 3.5 because that is, we are calculating the distance from here up to this point of our rotation. Then we multiply by the weight. That is how I got this value. Now, the second one, how did we go about this second one? As simple as it is, we just said, okay, this is a triangle, and the centroid of a triangle from here is 2/3. From this side is 1/3. So, that is very simple. I know you understand this. Now, if we go back there, we'll have 2/3 multiplied by 3.5. If we do 2/3 multiplied by 3.5, we are going to get the distance from here to this place. Now, the next one we are going to get is, if I do this, you will see that this arrow now is showing you distance x1, x2 to this point. Now, the next one will show you, okay, now, okay, let's not go there now. Let's not go to that one. But if I've settled this one, if I click again, let me just get everything out so I can explain. If I click again, you see that this particular one I wrote, Rankine, is 102. And this 102, we have calculated it already in the last slide. Somebody will ask, where is the 102 coming from? We calculated it from the last slide. So in the last slide, if you go back, you can see that is the lateral earth pressure, lateral earth force calculated using Rankine method. If you want to find the resultant is going to be acting at half. So you see, half of the length or the height of the wall. That is where we have 6/3 multiplied by 102. And why is it negative? Remember that all these ones are going to go in a clockwise manner. Why these ones are going clockwise? This is going to go anti-clockwise. So, the simple explanation is this. While these other ones that I'm cleaning now is going to cause the wall to turn, to overturn. This is going to cause the wall to overturn. This one and this one is the one resisting the overturning. W1 and W2 is the one giving the wall stability. The self weight of the wall is resisting the overturning. While P divide the lateral earth pressure is the one causing the wall to turn. So you can choose the sign convention in any way you want, but just have to be consistent. The minus and the positive is just showing you, okay, this is the direction. It's not showing you that force is negative. So at the end of the day, if you punch this in your calculator, you should be able to calculate this. I hope you understand this. Now, the next one you will have is this value here stands for the value of the vertical force or the load, that is R. So if I now want to find the resultant, where is the moment acting, the resultant of the force in this particular stuff. You remember that when you divide the moment by the force, you will get the distance. That, like I said, moment of a force is force times perpendicular distance. So when you divide moment by the force, you will get the resultant. So this is going to be acting at 2 meters from this point. You do the same thing for columns. The same method, the same thing. The only difference is that the parameters now changed. Because now you, in columns method, you will now have two values for the earth force. One is the one acting as vertical, which is this one that has positive sign, and the one that we have already resolved as horizontal, which is the one that have the negative force. So if you go back to this last slide, you will see that we have already calculated this force, the vertical force, and we said it is something like 31.4. So what do you have to do? The vertical force is just acting here, is acting at this point of the wall. Remember that this vertical force is coming from, the vertical force is coming from the soil here. So it is acting just at the end, just at this point. So because it's acting just at this point, the distance is going to be from here to here, which is 4 meters. And that is how we got this one. We said 31.4 multiplied by 4. So again, what do you do? The next one you have 86.3, which is the horizontal force here. 86.3, you multiply by height, half of the height, which is 6/3. That is how we calculated and got this. So if you want to find the resultant vertical force for Rankine, the difference between this one and the resultant vertical force for Rankine, I don't know if you guys can see it because this is actually blocking the place. Resultant vertical force for Rankine is now going to be 324 plus 31.4. Where did we get 31.4? 31.4 is the vertical load because of the friction between the wall and the soil. The friction is going to contribute vertical load, which is going to help to resist the wall from sliding, and is also going to contribute the horizontal component of the force, which is going to increase the chances of the wall to collapse.